You are looking at a ship the size of 4 city blocks that weighs more than 50,000 tons of solid steel. Even with all that weight, the massive structure stays afloat on the surface of the water. Most people assume that a single hole in the side of a hull like this means the end of the story. We've all seen the movies where water rushes in, the ship goes down, and everyone panics. But that is not how these machines actually work, and the reality is much more interesting. We need to figure out what is really stopping the ocean from taking over when things go wrong. To understand how modern ships are built to survive today, we have to go back to the most famous shipwreck in history. A modern cruise ship can have its entire front section flooded with seawater and still keep sailing. The Titanic wasn't sunk by one hole. It was sunk by a design flaw that engineers had actually already identified before she sailed. There is a hidden structure inside every large ship that most passengers never see, and it is the only reason you survive if something goes wrong. Today's cargo ships are divided into so many sealed sections that flooding one compartment barely changes the math at all. In April of 1912, the RMS Titanic set off on her maiden voyage as the largest ship ever built. She stretched more than 882 feet long and weighed over 46,000 tons. The engineers divided the inside into 16 separate watertight compartments, sealed sections running the full length of the hull. If water got into one section, it was supposed to stay trapped there while the rest of the ship stayed dry. The press called her unsinkable. Then she hit the iceberg. The iceberg didn't punch one clean hole. The impact buckled the steel plates and popped rivets across a long stretch of the hull, so water poured into 6 compartments at once. The designers had calculated the ship could survive 4 flooded compartments. 6 was a number she simply could not handle. The reason those 6 compartments became a death sentence came down to one critical design flaw. These internal walls, called bulkheads, only went up to a certain deck, instead of reaching all the way to the top of the ship. As water filled one compartment, it reached the top of the wall and spilled over into the next one like a waterfall. The Titanic's safety walls stopped just a few feet short of where they needed to be. That gap is what killed 1,500 people. If the internal walls had been just one deck taller, the ship would likely have stayed afloat long enough for everyone to be rescued. Engineers actually knew the compartment design had limits before the maiden voyage. Nobody acted on it. The unsinkable label wasn't an engineering claim, it was a marketing decision that cost lives. Think of an ice cube tray. Fill one slot and tip the tray slightly. The water doesn't stay put. It spills over the divider and fills the next slot in line. That is exactly what happened to the Titanic as she began to tilt. On top of that, the ship had no continuous double hull, meaning the outer steel skin was the only thing between the passengers and the open ocean. The Titanic didn't sink because ships are fragile. It sank because its compartmentalization had a literal ceiling. Engineers spent the next 100 years making sure that exact failure could never happen again. A modern ship's hull contains hundreds of individual sealed cells. Most of the crew has never seen the inside of most of them. The double bottom on a modern vessel is so effective that a ship can scrape across a reef and the passengers won't even know it happened. There is a set of international laws that legally requires every passenger ship to survive flooding in at least 2 compartments at once and still keep moving. Some military ships are built to absorb torpedo strikes and stay in the fight. The same principles are now used in commercial shipping. Here's the clever part. A modern ship hull is not one giant hollow shell. When you strip away the outer steel plating, you see a honeycomb of hundreds of isolated cells and sealed rooms. These watertight walls run the full width of the ship from floor to ceiling. No ice cube tray problem. These walls are called watertight bulkheads, and they work differently than the ones on the Titanic. Modern bulkheads extend all the way up to the weather deck, the main exposed top deck. Water physically cannot reach over the top to flow into the next compartment. It stays locked in place. Underneath the ship, engineers add what's called a double bottom. 2 layers of steel on the floor of the hull with a gap between them, usually 1 to 2 meters deep. When a ship scrapes a reef, the outer skin might tear, but the inner skin holds. Water fills that small gap instead of flooding the main hull. That space between the skins also carries ballast water, seawater that engineers pump in and out to control how the ship sits in the water. We'll come back to that in a moment. There is a specific international standard that ties all of this together. Under the Safety of Life at Sea Convention, known as SOLAS, modern passenger ships must stay afloat and remain stable even if any two adjacent watertight compartments flood completely. On larger ships, the requirements go even higher than that. 2 full compartments of seawater can pour into a modern passenger ship, and it is legally required to stay upright. That is not a goal, it is the minimum. The Safety of Life at Sea Convention was written directly in response to the Titanic. Every rule in it exists because of what went wrong that night. If you enjoy understanding how the hidden engineering of the world actually works, hit subscribe. We break down one mechanism at a time, every single week. Some of the largest vessels afloat today could absorb the equivalent of an Olympic swimming pool worth of seawater and barely change their trim. This is known as the 2-compartment standard, and it is a legal requirement, not a suggestion. Every ship is designed and tested against this rule before it ever touches the water. When a breach opens, sensors detect the water and automatically trigger the watertight doors to seal off surrounding sections. The ship might settle slightly lower on the flooded side, but then it holds its position. This is when the damage control teams move in. These are trained crew members whose job is to shore up bulkheads, run portable pumps, and move ballast water to keep the ship balanced. The physical structure buys the crew time, and they use every second of it. The U.S. Navy saved a destroyer from sinking in 2017 after a collision tore open a massive hole in the hull. Damage control teams sealed the compartments in minutes. On a modern warship, every single sailor learns damage control in their first week of training. It is treated the same as learning to fire a weapon. Portable pumps on large ships can move thousands of liters of water per minute, fast enough to outrun a flood if the compartments hold. The physical structure of the ship is only half the equation. The other half is the crew running toward the problem instead of away from it. If the Titanic had been built to this standard, with full-height bulkheads and a double hull, the flooding from those 6 breached compartments would have been contained. The ship likely would have stayed afloat long enough for every single person on board to be rescued. That is the real-world difference that better engineering makes. We still need to answer the most basic question. How does a ship made of thousands of tons of heavy steel float in the first place? A solid block of steel sinks instantly. But reshape that exact same block of steel, and it will float without any problem. Shape is everything. Archimedes figured out the physics of floating more than 2,000 years ago in a bathtub. The same math is used to design aircraft carriers today. A fully loaded supertanker displaces so much water that the downward push it creates can actually change the depth reading of the harbor it enters. There are 2 invisible points inside every ship that engineers obsess over. If those 2 points drift too far apart, the ship rolls over, no matter how big it is. Floating is not about what the ship is made of, it is about the shape. Drop a solid steel ball into the ocean and it sinks. Take that same steel, roll it into a bowl with hollow space inside, and it floats, because the shape pushes water out of the way. The weight of that pushed-aside water is what holds the ship up. This is Archimedes' principle. A ship floats because it displaces a weight of water equal to its own weight. The shape does all the heavy lifting. Every ship has 2 invisible points that control its stability. The center of gravity is where all the ship's weight pulls downward. The center of buoyancy is where the water pushes back up. When those 2 points line up, the ship stays upright. When one side floods and the ship starts to lean, called listing, a force called metacentric height kicks in. Think of it as the ship's snapback force. Engineers design vessels with enough of it that a partial flooding event won't tip into a full capsize. This is why ballast water matters so much. Pumping seawater into tanks low in the hull pulls the center of gravity down, which increases that snapback force and makes the ship much harder to tip over. And when one compartment floods, it does not erase the buoyancy of every other sealed section. The rest of the hull is still pushing water aside and fighting to stay on the surface. The math still works because the engineers planned for exactly this kind of failure. Modern ships don't stay afloat by accident. Every bulkhead and sealed compartment is a direct answer to how ships used to fail. The Titanic showed us exactly what happens when your walls don't reach the ceiling, and every vessel built since then has been a direct fix for that mistake. If you want more breakdowns of the hidden logic inside the machines we use every day, hit subscribe. We do this every week. Thanks for watching, and I'll see you in the next breakdown.